Hey everyone. So we've spent a lot of time talking about how to design digital hardware, right? But it turns out the design, well, that's only half the battle. Today, we're going to dive into the hidden but absolutely critical world of verification, which is really just the process of making sure those brilliant designs of yours actually work.
You know, I love this quote because it just hits the nail on the head. It perfectly captures the fundamental challenge of pretty much all engineering. You can have the most beautiful, elegant design on a whiteboard, but getting it to work correctly in the real world, that's a completely different beast. And that gap right there, between theory and practice, that's where the real work begins.
And bridging that gap is, honestly, one of the biggest challenges in digital design. It's a whole process of relentless, systematic testing that goes by a very specific name.
Yeah, and this slide really highlights a super important distinction. On one hand, you've got validation, which asks, are we building the right thing? Does the market even want this? But verification, which is what we're focused on today, asks something way more fundamental. Are we building the product right? Does the hardware we created perfectly match the blueprint, down to the last tiny detail, with zero bugs?
And to understand just how vital this is, get a load of this number. In really complex hardware projects, verification can eat up more than half of the entire project's schedule. You might be asking, why so much? Well, it's because a modern chip can have billions of possible states. It's what we call a combinatorial explosion, and it's literally impossible to test every single one. So this isn't some afterthought. For a lot of teams, verification is the main event. So if you're spending all that time, how on earth do you actually do it?
Well, you do it by building something called a test bench. Here's a great way to think about it. Imagine your design, let's say it's that CPU we've been talking about, is a cook in a restaurant kitchen. The test bench, that's the health inspector who comes in to make sure every single dish that leaves that kitchen is absolutely perfect and, won't make anyone sick.
So what is it, technically? A test bench is basically a piece of VHDL code that you wrap around your design. But here's the kind of wild part. It doesn't have any external ports. And you might wonder why. Because it's a totally self-contained universe. It generates its own inputs, it controls its own timing, and it checks its own outputs. It's the director, the actor, and the critic all rolled into one.
And this analogy just illustrates the components perfectly. So first up, you have the stimulus generator. That's the inspector ordering a dish right off the menu. It creates all the inputs for our design under test, or DUT. That's our cook. Next, the monitor watches the output. That's the inspector's taste test. And finally, and this is the most important part, the checker compares that output to what was expected, just like our inspector comparing the dish to the official recipe book to see if it was made correctly.
And just like any real-world inspection, the methods we use for verification have gotten a whole lot more sophisticated over time. We've moved way beyond just staring at a screen and hoping for the best.
We can really break down this evolution into 3 key levels, starting from the most basic and moving all the way up to what the pros use today.
Okay, so back in the early days, verification was literally just this, the eyeball test. An engineer would run a simulation and then just stare at dozens of these signal waveforms scrolling across a screen, trying to spot a mistake. I mean, you can imagine, with millions or even billions of clock cycles, this is not just tedious, it's pretty much impossible to do accurately. Human error is almost guaranteed.
So the next big leap was figuring out how to get the simulation to check itself. In a language like VHDL, we can use this really powerful command called ASSERT. It's basically like telling the code, hey, I expect the answer to 2 plus 2 to be 4. Assert that this is true. And if it's not, if you get 5, sound the alarm and stop everything. This was a total game changer, because now the test bench itself flags the error the very instant it happens.
And this brings us to the industry gold standard, the golden model. Just look at this setup. The test bench, our inspector, now has more than just the recipe book. It has a golden version of the dish made by a master chef. So what it does is it feeds the exact same inputs to both our design and this perfect reference model, and then it compares their outputs, clock cycle by clock cycle. Any difference, no matter how tiny, means a bug has been found. It's incredibly powerful.
But here's the thing. Simply running millions of random tests isn't enough. The most dangerous, sneaky bugs, they don't hide out in plain sight. They live in the dark corners of the design. This means verification isn't just about quantity. It's about running the right kind of tests. And those right tests are the ones that check for corner cases. So what are these?
Well, there are all those tricky boundary condition scenarios. What happens when your registers are completely full? What happens when you try to add the largest possible number to 1 and it causes an overflow? Or when you try to do something that shouldn't even be possible, like dividing by 0? A really solid verification plan specifically targets these edge cases to find those subtle bugs that random testing might just miss for years.
And all of this leads to a pretty profound, almost philosophical truth about verification. No matter how many millions or billions of tests you run, you can never prove a design is 100% bug-free. All you can ever do is show the presence of bugs, not their absence. So verification isn't really about achieving mathematical perfection. It's about systematically hunting for errors to build confidence in your design.
So this raises the ultimate engineering dilemma, right? If you can never truly prove a design is perfect, how do you know when you're done? How does a company ever decide it's time to ship a billion-dollar chip? The answer? Well, it's a really complex balance of test coverage, risk assessment, time, and money. And getting that balance right is one of the toughest challenges in all of modern technology.